We're continuing section 5.1. We're actually going to continue from where we left off last time. So let's just go back right there. Last time, in our last video, we defined the angle in between two vectors in Rn. And like we said, in R2 or R3, this makes physical sense. In Rn, it doesn't really have a physical embodiment, if you will, but don't worry about that. We want to define this mathematically. We will see. Well, I won't say anything. I'll let you see as it goes on. The angle theta is defined using u dot v, the dot product, over magnitude u times magnitude v, and that this big giant quotient here is cosine theta. Now, once you know cosine theta, then you could figure out theta itself. And we have restrictions that theta is between 0 and pi. So theta is just going to be the arc cosine of whatever this fraction is. This is an interesting remark here. The angle between the 0 vector and another vector is not defined. And that makes a lot of sense. First of all, it doesn't really make sense. It makes sense for it not to be defined. It doesn't really make sense physically. Physically, how do you have an angle between, a 0 vector is kind of like 1 point. So how do you have an angle between just 1 point and a line? So it kind of physically doesn't make sense. Plus, if you notice in the formula, the magnitude of the 0 vector is 0. So you'd wind up having 0 on the bottom of a fraction, which also makes it undefined. So it's, doubly undefined, if you will. Let's find the angle between two vectors now. Now that we have this formula, so we have a vector in R4. This is 4-dimensional. -4, 0, 2, -2. And they have another vector, 2, 0, -1, 1. So using the formula, cosine theta is u dot v over mag u times mag v. And u dot v winds up being -12 because it's -4 times 2 plus 0 plus 2 times -1 plus -2 times +1. And that comes out to -12. -8, you can figure that out. And the magnitudes are rad 24, rad 6, which becomes rad 144. And rad 144 is 12 itself. So I get -1. Now, when is the cosine theta -1? Well, that's for 180 degrees. That's when theta equals pi, which is 180. And 180, when two vectors are 180 degrees, that means they're like an exact opposite direction of each other. And if you think about that, you can actually see it, because if I take vector v, multiply the entire vector by -2, so 2 times -2 is -4, 0 times -2 is 0, -1 times -2 is +2, and 1 times -2 is -2. So notice that vector u is equal to -2 times vector v, which makes sense for it to have the opposite direction. Now again, opposite direction doesn't have much meaning in 4 dimensions, but somehow the math works out consistent. So these definitions kind of work out in a very cool way. Anyway, let's talk Turkey here. Well, it's just an expression. So the magnitudes are always positive. We discussed that already. So that means that u dot v and cosine theta, if one is positive, the other is positive, and if one is negative, the other is negative. So either they're both positive or they're both negative, because I'm taking u dot v, dividing it by a positive number. So in other words, u dot v and cosine theta are always going to have the same sign. And we know that cosine is always positive in the first quadrant, and it's always negative in the second quadrant, which means that if the dot product is positive, the angle is in the first quadrant. If the dot product is negative, the angle has got to be in the second quadrant. And that's all this angle. That's all. Remember, we're only restricting the angles to be between 0 and 180. So that's all. That's the only choices we have is quadrant 1 and quadrant 2. Anyway, here we have some nice little pictures here. So when theta equals pi, and cosine theta equals -1. So if we do this whole formula and we get cosine equal to -1, that means theta is equal to pi. If we get a negative cosine, that means theta is between pi over 2 and pi, meaning it's an obtuse angle or it's in the second quadrant. If cosine theta, if cosine theta, meaning if this expression winds up being 0, then that means cosine theta is 0, which means theta equals pi over 2. And if we wind up getting a positive cosine, then that means that means cosine theta is positive, which means the angle is in the first quadrant. So it's between 0 and pi over 2. And finally, if we get cosine theta equals 1, meaning that the top and the bottom of this fraction are the same, then that means theta equals 0, which would again indicate that one vector is going to wind up being a positive multiple of the other vector. So we could tell a lot just based on the dot product. If the dot product is negative, 0, or positive, we can tell right away these acute, obtuse, and so forth, or right. And let's look at this middle case right here. This case right here, when the dot product is 0. So the dot product is 0. The vectors are perpendicular. Now we're gonna now perpendicular, I guess, is not fancy enough of a word, so we have to make a new word called orthogonal. And that's me being cynical. But when we do vectors, here's a very great. Here's how we define an orthogonal vector in Rn. See, in R2 and R3, then of course orthogonal makes sense. It's at a right angle. But what's a right angle when you're out in 4 dimensions, 7 dimensions? What does a right angle be? What if the dimensions aren't even dimensions? Like I said, dimensions don't have to be space. They could be temperature. They could be pressure. They could be, who knows, a lot of things it could be. So basically, if I have two vectors and their dot product equals 0, so by definition, I'm going to call that orthogonal. So now, this is a really interesting thing here. This little comment on the side here, that even though we said there's no such thing as the angle between the 0 vector and another vector, there is nonetheless we do say that the 0 vector is orthogonal to every vector. In other words, we can extend the definition of orthogonality because it's very easy, because I have the 0 vector dot anything else is going to give me a 0. So it makes sense from the formula that the 0 vector will work, and we're just gonna extend that concept. Even though there's no such thing as an angle between a 0 vector and another vector, we can and do still say the orthogonality. We discussed the orthogonality of a 0 vector, and we say that the 0 vector is orthogonal to every other vector. So I think I made my point. Let's look at some examples of orthogonal vectors here. So here we have a very simple one, example 9. Well, here we are in R3. So 1, 0, 0, and V vector is 0, 1, 0. Well, these are orthogonal by the formula, because U dot V is going to be 1 times 0 plus 0 times 1 plus 0 times 0. And of course, that equals 0. Now, by the way, it makes a lot of sense because, in R3, because this is really on the x-axis. This is a unit vector on the x-axis. This is a unit vector on the y-axis. And we know the x-axis and the y-axis are perpendicular. So it physically makes sense. And the formula sort of, bears that out, or it works in the formula as well. But now we're looking at R4. R4, again, there's no physical embodiment of this. So if you want to find a dot product, if you want to show that these two vectors are orthogonal, we have to do the dot product, and we get 3 times 1, 2 times -1, -1 times +1, and then 4 times 0. And that comes to be 3 minus 2 minus 1 plus 0, which equals 0. So these two vectors, whatever that means physically, don't worry about it. These two vectors are orthogonal according to our definition of orthogonality. Now, to make the just in case this is all easy for you, let's see if we can make it a little bit harder. And let's find all vectors in R2 that are orthogonal to U where u is the vector 4, comma 2. So we're not just taking two vectors and testing them to see if they're orthogonal. We want to find in general all the vectors that are orthogonal to 4, comma 2. Well, let's let v be the missing vector, so to speak. That's what we're trying to find is v, and the components of that are v1, comma v2, and let's say v is orthogonal to u. So by definition, the dot product of u and v is 0, which means 4v1 plus 2v2 equals 0. But that implies that 2v2 is equal to negative 4v1, and v2 is then equal to negative 2v1. So every vector orthogonal to 4, 2 is going to be of the form t comma negative 2t, or I could say it's t times negative 1 comma 1 comma negative 2, t of course being a real number. And by the way, I don't want to get you all too crazy, but this is a vector space. I wonder if it's always going to work like that. That's something that we always like to investigate. Now, I want to get to another thing. There's a very famous inequality called the triangle inequality. And it's called the triangle inequality because it kind of, is based on a physical triangle. If I have basically the triangle inequality with triangles tells me that the third side of a triangle is going to be less than or equal to the sum of the other two sides, which is another way of saying the shortest distance between 2 points is a straight line. And we know that if you have a vector u and a vector v, so u plus b winds up being the diagonal of this parallelogram, but it's also the third side of this. If I just look on the right side here, it's like the third side of that triangle. Let me see. I wonder if I could draw a little thing here. Just to... No, it ain't working. Okay, forget about that. So, well, we tried. Oops. Okay. Anyway, so the magnitude of the vector u plus v is going to be less than the magnitude of u plus the magnitude of v. And we want to extend this. We want to say that this is true of all vectors. Again, we see this from the picture, but we want to extend this now to all vectors in Rn. And when you extend it to all vectors in Rn, pictures ain't going to do the job because Rn, there really are no pictures in Rn. Sometimes we draw pictures for Rn just to help us kind of visualize it, but really there's no such thing as a picture of Rn. Anyway, here is the proof of this theorem, and it really just comes from the properties of dot product, which sometimes we give these lists of properties and seem, oh, they're so boring, just a long list of properties, but these properties are going to help us prove some phenomenal, amazing things. Anyway, so let's look at the magnitude of u plus v. Well, we know that if I square the magnitude, that winds up being u plus v dot u plus v. That's one of our properties. And now I could distribute this out, and I wind up getting with u dot u plus 2u dot v plus v dot v, which is mag of u squared plus 2 u dot v plus mag v squared. Now again, magnitude is just a number. It's just a real number. A dot product here is just a real number, and this magnitude is just a real number. And of course, this guy here is also just a real number. These are all real numbers now. It's always good to. It's always important when you're doing. I'm saying kind of as a side point, but when you do linear algebra, you have numbers, you have vectors. It's always important to know is this a vector? Is this a scalar? Is this a number? Is it a R2, R3, R7? Like what dimension are we talking about? It's always good to keep it, not just good, but very, very important to keep track of just what we're dealing with. Anyway, this is now, so this is less than or equal to the magnitude of u squared plus 2 times the absolute value of u dot v plus the absolute magnitude of v. Now, how did the equal turn into a less than or equal? Because the dot product here could be negative. When I take the absolute value, it would make it positive. If that's the case, then a negative quantity makes something smaller than adding a positive quantity. If the dot product was already positive, then it would just be equal. So nothing's changed. Anyway, using the good old Cauchy-Schwarz inequality, which we learned, u plus v squared now is less than or equal to u mag of u squared plus 2 u dot v plus mag v squared, and that is less than well, again, this is just the same, but this part here, we know the absolute value of u dot v is less than mag u times mag v. That was what Cauchy-Schwarz helped us with. And this is equal to mag u plus mag v squared. And now that means these are both non-negative. So that means I could take square roots of each side and still preserve the inequality. So that means that the mag of u plus v is less than or equal to the mag of u plus the mag of v. And it all, because I have these lessons here, so it all works out. It all works out beautifully. And this is a very beautiful thing. Again, if it was just on the plane, if it's geometry, it just, you know, it's quite obvious that the third side, that adding two sides of a triangle is going to be greater than or equal to the third side. So that is the story here. Now, if you now in this proof, we got this guy right here, u plus v squared is u squared plus 2uv plus v squared. Now, what if this middle term here, what if that didn't exist? What if theoretically, if that didn't, what if this little part here didn't exist? Well, that could happen if u dot v is 0, which would mean that the two vectors are orthogonal. So now we have, if the two vectors are orthogonal, we have sort of a generalized version, or a vector version, if you will, of the Pythagorean theorem. Because remember, in R2, we have u, v, and then u plus v is like the third side of that triangle. Of course, in R5 or R20, you know, it doesn't necessarily have a physical triangle to it, but we see kind of a vector version, or the book calls it an extension of the Pythagorean theorem into Rn with vectors. And I think it's pretty cool and awesome, because there's nothing, to me, there's nothing cooler and awesomer than taking an old concept and like sort of redefining it, or not redefining it, but extending it, and sometimes you have to define it properly to a more abstract or a higher or a more broad scenario. Anyway, there we go. Pythagorean theorem in outer space, if you will. By the way, where do otters come from? Outer space, get it? Okay. Now, dot product and matrix multiplication. You may have noticed that there's a great similarity between how we do a dot product and how we do a matrix multiplication. It's kind of the same, you know, do the first component times the first component. You know, we do a matrix multiplication, we're taking a row and a column. So it's the first element of this row times the first member of this column, second, third. So dot products and matrix multiplication is kind of the same process. And I guess you could define it that way, because I could say that u dot v is u transpose, the matrix of u transpose times v. Notice here's u as a column and v as a column. So now I'm turning u into a row by transposing it. And now if I do the matrix multiplication, I essentially get the same thing as the dot product. So that's kind of it's kind of cool. And so therefore, if you want to take a dot product of two vectors, I could rewrite it as a matrix multiplication, and I get 6. And I want to take the dot product of these two vectors here, and I rewrite it as a row times a column, and I do a matrix multiplication, and that's -5. And now you may say, like, who cares? What's the point? Well, there are a lot of properties of dot products that are direct consequences of the corresponding properties of matrix multiplication. And you know, there's some. It's just the concepts intermingle or commingle, or I don't know what the word for it is. Anyway, that is the end of section 5.1. Yay! Next, we'll see you next time. I guess it's been loads of fun, and we'll see you next time.